Thank you very much. And I'm aware I'm between you and the break, so I won't talk chemistry, neither maths, neither particle physics, although I come from CERN. I do come from the CERN Fire Safety Engineering team. That's an in-house service that we created about 1.5 years ago. It existed before, but we created it as a team. And it's an in-house service at CERN to provide a fire safety response to this unique facility that is CERN. I will talk about it a little bit, and I would like to present to you today a particular part of a performance-based design assessment that project that we conducted recently, and I would like to foster some discussions on the usage of FED for quantitative risk assessments, which is one of the research lines we are developing within our team. So first of all, let me acknowledge my colleagues Arnalik and Oriol who helped me, or we developed this work all together. So just to contextualize what I'm going to be talking about, that CERN is an international organization. It sets on 2 different countries at the same time, so it's partially in Switzerland, partially in France, so partially in Europe, partially outside Europe or outside European community. It has about like 10,000 people on campus. We speak 2 official languages. That's not really important regarding fire, but what is important regarding fire is that we have about 100 kilometers of underground galleries for particle acceleration facilities. So actually our challenge is to provide safety or to check the safety levels on those underground galleries with one-of-a-kind equipment that is being developed only for CERN. So our flagship experiment is called LHC, Large Hadron Collider. It's a 27-ring tunnel around 130 meters underground. And it looks like this. So this is the larger ring we have right now. And the idea is that to provide safety to CERN, to underground and to the experiments, to the caverns, we have our own regulation. That means that we do not have necessary to apply any regulations out there, so we can develop our own regulations and apply it underground. Even though if we would have to apply any regulation out there, which kind of regulation do you choose for a ring tunnel? Like, that's not really a rail tunnel, not a road tunnel. So then we just go with the performance-based approach now, and we try to answer these questions by means of performance-based design. But I'm talking about this LHC project, but actually what I will talk to you today is about a FCC project. That's the new project that it's in a study phase actually, of the new tunnel that will or may be constructed around CERN, and that will be around 100 kilometers tunnel, so perimeter tunnel, about 300 or 500 meters underground. And why does it change? Because the tunnel is kind of flat, but the ground is not flat, so you have different distance to the surface. And actually I got involved to CERN to work on the performance-based design for this future collider, as it's called, future circular collider. So within this project, we were looking at fire safety on this tunnel, and we set out like the performance-based design approach as it's stated in different guidelines. So we started from the beginning. We iterated the trial design to look at the robustness and the safety of this trial design. Even we kind of peer review it with other accelerator facilities, some of them in United States as well, some of them in Europe, just to help having some feedback around this process. So today I will focus though in a specific performance or at a specific goal. We obviously look at different safety objectives. We look at life safety, environment, property, and continuity of operation. But I'll focus today in life safety, and more specifically, not on occupant safety. For occupants, we define occupants as all the people that can evacuate by themselves. Those are occupants, and we took different thresholds as they are stated in different guidelines. We saw them yesterday already. We also look at the acceptance criteria for firefighters. We have an in-house fire department, and we would like to provide them which would be the conditions they will have to face in case of an event down there. So we look at these acceptance criteria. But what I'd like to talk about today is about the victims. As victims, we define the people that cannot self-evacuate by themselves. So people that are stuck underground on the tunnel, or they're impeded for whatever reason. And as you can already see, and Daniel mentioned it yesterday, this RSET ASET strategy doesn't really work here, or won't work here, because we are sure that if someone is stuck in the fire compartment, the visibility will go to 0. But as Daniel stated yesterday, and I fully agree, visibility don't directly kill you. Like, nobody really gets killed due to visibility. You get killed due to like fire, due to like heat, due to like toxicity, but not due to visibility. So we need a further assessment, a more detailed assessment. And that's why we go to the FED assessment. And at some point, we would like to go on a step forward and link it to a risk assessment. Because when we talk about FED, we are already talking about probability of something occurring. So for us, it was kind of like a logic step, just moving forward this FED to integrate it to a risk assessment. So I will just quickly walk you through the PVD process, just so you see a little bit what I'm talking about. When I'm talking about the FCC study that we conducted, we designed 3 different fire scenarios. Well, the first one we call fire 1 was a cable tray fire. Second scenario was a drum fire. So these large drums that are like lowered to the tunnel in order to install to cabling on the tunnel. And the QK fire, the fire number 3, that's the transport mean. Those magnets, actually these 27 kilometers, even the 100 kilometers will be full of magnet, superconducting magnets. Those weigh a lot, more like several tons, and they need to be like transported by transport means, and those transport means have to be electric. So there is definitely a fire hazard on there. So those are the 3 fires we selected. I won't focus on that, but we came up with the heat risk of those fires. And this is the cross section that we get. As you see, this is a 5.5 diameter tunnel that has an even, let's say, ground, because, okay, due to the machine, this is what we call the machine. This is the pipe that is there in the tunnel. It has this even surface, and then we have compatible ventilation. Luckily enough, we got compartments every 400 meters. So we will reduce our simulations in these 400 meters. Actually, I never thought of having 100 kilometers simulated on FDS with a boundary condition that is a ring boundary condition. But we rather go for a partial simulation of these compartments. And the first aim was to try to check which was the required air supply / smoke extraction strategy. So we had to play a little bit and to launch multiple scenarios to try to see which was the best design. And actually the design we at the end chose was, together with the ventilation group, it was that during normal conditions we had this translational longitudinal ventilation scheme. So we are pushing air on different inlets. We are extracting air using the tunnel as a pipe, so it's a combined strategy, and we keep this what we call emergency duct here just in case. In case of fire, we detect the fire in a compartment. This is a 400 meters compartment. We detect the fire, we close the doors of this compartment and the adjacent compartments. We create a pressure cascade in order to further confine the smoke in this compartment, and we start extracting a certain amount of air on this smoke extraction duct. That was the strategy that was developed, and we had to put numbers on there using FDS to see, well, FDS and seeing the evacuation velocities to see what was the scenario or the smoke affectation to people. So, as I was saying, we set up the model. We set up only a 400 meters scenario, but that already went up to 2 to 16 million cells. Luckily enough, at CERN we have huge high-performance computing, so I had access to 1,000 cores computer to run this simulation, so I could play a little bit with that, even though I tried to reduce it to 2 million cells, because if there is no need for computation. So not because we have it, we should use it for the fun of it, no? We set slices, we set sensors. Actually, the strategy to setting sensors is because we had a post-processing tools afterwards reading those sensors. But there is something missing here. I'm talking about the FED. To account for FED, we need to account for an evacuation model. So we needed an evacuation model, and actually here the easy thing is that the 1D approximation of evacuation model is quite certain here, because the tunnel is 1D. So either you go to one direction or you go backwards, well, backwards to the other direction. But we went for a 1D model. We developed it with the help of Lund University, Silvia Ares and Enrique Ronchi. And actually we took data from Rios, as well on the visibility, on the walking speed through through reduced visibility, and we set some yields. Here is important. I only set yield for CO2 and CO, and the reason is that I had no idea what will be the material that will be used in 50 years to be down there. So it was hard to get a yield from hydrogen cyanide. Although I know that that's a limitation, and after seeing yesterday's Daniel, a big difference on the impact of using those other yields, it would definitely need a revise there to see which is the impact. But actually, the data that's going to be produced here is only just to explore which is the capacities of this FED strategy as a risk index. So we also set this hyperventilation term, which means that you breathe more when there is too much CO2, and we set an imparted human speed of 1 meter per second that was reduced according to visibility. So just for those that are not used to data visualization in tunnels, we have a nice way of visualizing this data because we already have 1D geometry. So if we look at the tunnel, we can stack what is going to happen on the y-axis. So we have time on the y-axis. So we stack the people moving and the smoke propagation in the y-axis, and in the x-axis we have one direction. So we have x direction. So we choose a given y, so a given depth in the tunnel, and we choose a given height in the tunnel. And we will change this height because that has an important effect there. But the thing is that then we can say this is the area that there is smoke, and we can keep tracking people. So our 1D model will tell us where are the people over time located. That's easy. And for the victims, it's even easier because the victims, those that are unpitied occupants, they do not move. So actually, there is no 1D model for them. Like the model is pretty simple. So we can create those plots out of the FDS simulation. So that's visibility, for example, and visibility at 2 meters. And we can create exactly those same plots, time stacked over length. And we can plot on here the people moving out. And then we can count like all the visibility along this evacuation path, or the FED, we can account any, like the thermal FED, we can easily account for. So we did that, and we did that for occupants. And for occupants, we find a good design. We find the design that even though we were choosing different pre-movement times according to different distribution, they were safe. They were safe in terms of visibility, in terms of temperature, and as it was said yesterday, if you are safe in terms of visibility, you know that you are safe in terms of FED, because if you don't see smoke, there is no species that you will see. Obviously, there will be some material that will create toxic gases without soot, but it's not the case of general materials that we are using. But for victims, we need to go for FED, as I said, to buy more time. Let's say, I don't know if buy more time would be the proper concept, or like to be more detailed and see which is the correct consequences, or the realistic consequence to the people. So here, as I said, we only focus on the CO and CO2 effects. So we neglected the rest of the species due to limited knowledge on the material, and we explore these simulations. Unfortunately enough, if you have been using FDS in tunnels, there is some point where your fire gets ventilation limited, and you have pressure issues, and then the simulation gets unstable, and after some time it's highly probable that your simulation will crash due to numerical instabilities. And that's actually what happened, and if you try to simulate 1 hour, it's highly probable that will happen. Even though this happened to some of the fires, we had already one run that went out to 55 minutes. So we can already explore the data that's fed of the occupants being standing still in a place, or victims, sorry, not occupants, victims. And this is the case where we got most of the data, and we could show which was the trend of this curve. So the curve really followed an exponential curve. So with this, we went for the other scenarios where we were lacking some data, and we extrapolated the same law. So we put the same law, and we extrapolated the values for the same law. So let's say with limited data, we could extrapolate it on the feature. And I'm pretty, let's say, convinced of this strategy, because at some point we are reaching a level of FET which kept not a level of FET, a level of toxicity that is kept constant. So the FET is being accumulated in a homogeneous trend, let's say. So we have the FET, and there is still one piece missing here, which is okay, I said the 1D model is pretty simple because the occupants are not moving, but they're going to be rescued, and they're going to be rescued by the fire service. So we had to model the fire service intervention into this infrastructure. And as I said, CERN has an in-house fire service, but for this FCC, we had to come up with a probable distribution of this fire service. So first of all, we said that when they get to the compartment and they can use transportation means to get to the compartment, they have this entry time to get to the victim and to take the victim out. And for this walking speed, there were some tests performed in the fire brigade. They were blinded here, so they couldn't see anything. So we could account for the advancing speed of the fire brigade in the real tunnel. So that's the real tunnel. That's what the 1 meter space that they have to move. And we also assume that they will carry this safety mask. So that means that as soon as they reach the victim stops inhalating FET. So the FET is stopped as soon as the fire brigade reaches each victim. But obviously we wanted to account for more than one victim, saying that there are more than one people that needs help. So as there are only 2 firefighters that they have to go to the victim, go back, go to the second victim, go back, and that's the process we will account for. So having those hypotheses, we can look at different fire brigade strategies. So having firefighters already down in the shaft, having firefighters ready in the surface area on the shaft, or having firefighters ready every 2 shafts. And that will give different what we call show-up time. And this show-up time will depend on the distribution of those firefighters. So with all this data, we can go and compute which is the FET of these victims that are being rescued. And the only thing we need to know here is to understand what FET comes from. And FET comes from a log normal distribution, so I guess that's a convention, because otherwise that's not only a log normal distribution, it's the log normal distribution with first moment 0, second moment 1, so it's like the standard log normal distribution. And that's why we got these values that were shown yesterday, or the values used for FET. That means that FET equals 0.1 means 1% people of dying or being incapacitated, 0.3 means 11%, 1 means 50% of people being incapacitated or affected by the toxicants. So we have these data, so we have the PDF and the CDF of this distribution, so we can say once I get the FET of the victims, I can transfer this into a probability of these victims of dying or being affected by this FET, and we can do this thanks to the log normal distribution. So we extrapolate and we use whatever values we get for FET, and then we compute this to get the expected number of fatalities given the number of victims, given the number of people embedded in the tunnel. We can say how many of them are likely to be casualties. So now we do have all the ingredients, and we can go and check all the fires for the different configurations we got. So those are the 3 fires. This is again the FET of each victim, but at the time the firefighters reach them, and this is the dying probability of each of them, and this is the accumulated dying probability given the number of victims. So if you see here like a 45 degrees line, that means that 1 victim gives 1 casualty, so that means you are not rescuing a life, or it's highly unlikely that you rescue a life on any of those people stuck there in the tunnel. So we can run those analyses for different positions of the victims, obviously, because I haven't said it, but that you have to assume a position within the compartment. So we can run this for different positions, and we can run this for different show-up times, and we can compare which are the results. I won't flood you with graphs, but we can do all these analysis, and after processing them, we can account for this table. And this table I put in a positive way. So I said potentially saved people, so not casualties, but people that you could potentially save. And you see that there are like most of the situations are really bad. So regarding Fed, most of the situations, by the time you reach the people, there are no chances or according to the Fed analysis, there are no chances that they are still alive. And as no chances, we mean more than 80% of probability of dying. And when they reach 80%, we consider that they're fatalities. So as a conclusion, the performance-based approach was a really sound approach for designing and for checking the performance. That's actually a conclusion, let's say a bonus, because I didn't prove it during my talk, but as I said, that's a partial part of a larger performance-based design project that we conducted. FDS was necessary to conduct this project because otherwise there is no way of calculating Fed. So simplified models for calculating Fed when you have like a ventilation scheme that is not a uniform ventilation scheme are not useful. There are some uncertainties on the way we use Fed. So when we extrapolate Fed out of these numbers that we normally use for thresholds, what is really the meaning of that? We've been asking this around, and we had problems on like really saying Fed equal to, what does it mean in terms of like dying probability? But that's definitely a way we think we should proceed to get a quantitative risk analysis. So we definitely think that's a quantitative index that you can use in order to compare different scenarios. And at some point, to get cost-benefit analysis, you need to compare different scenarios and get a sound index to compare them. And as a last slide, future work, we really want to use to further investigate on this Fed analysis. We know, and it was said yesterday, that it's highly dependent on how you characterize the fuel, and that's why we have an ongoing project to better characterize the fuel, including the yields, and as well, and this is this FERIA project, and as well the radioactive part of the fuel. And as a radioactive part, I mean, if you have a radioactive material that starts burning, you are interested as well of which is the radioactive part of this smoke being deposited and being transported around the tunnel, and that's a part that, or that's a necessary part that will be developed in this project FERIA that it's upcoming. And by this, thank you very much.
Thank you, Oriol. We have a few moments for some discussion. Does anybody have a question? Comment in the back?
Hi, thanks for the really good talk. This isn't directly related to the work that you presented on, but more of a general question. What fraction of the time are any of those sections of the tunnel that are just like your transport of particles actually occupied by people doing work?
So that's actually a good question that we posed ourselves. And the problem is that it can change a lot. It can change from nobody when there is when the machine is on. So when the machine is on, there is nobody. And it can change up to high people in a high rush when there is a stop of the machine in one day and they want to recable huge sections. So we had actually, we accounted for the last years, and there is an average density of people we could look at. And I don't have it by heart, but it's about, I think it was 10, 20 people by 100 meters. So that's the density of people you could expect. But it's nothing that, for these 100 kilometers, it's nothing that we get because, I don't know, maybe there is a problem. There is a lot of people working in the same spot because there is a big problem. They need like a lot of people there. So
right. I'm just curious. In a typical building, you're sort of planning for the building to be fully occupied at all times, and you sort of have to be careful about how you spend your money, where you want to provide your protection. But in a case like this, maybe if you can count on it only being occupied 1% of the time, you can concentrate your resources to one part of the tunnel in terms of firefighter response or equipment response. So just curious if it sounds like you guys have thought of that sort of aspect of this protection.
Yeah, definitely. Like not in this project yet because we don't have enough data. But for example, the caverns, which are where the experiment takes place, they are occupied more often than the tunnel section. So definitely they deserve like better for there.
Thank you.
Any other comments or questions? No? Well, thanks again very much.